have learned the various techniques of differentiation, especially chain rule, product rule, and quotient rule being the more advanced techniques. So at this stage, we have learned enough to be able to differentiate mostly any type of function that is required to be differentiated at the physics level, at least. Okay. So in today's lecture, we move on to the applications of differentiation. Okay. From the techniques of differentiation itself, move on to the applications of differentiation in various different types of situations. Okay. Also at this stage, I hope most of you have been able to complete up to assignment 3 or worksheet 3 completely all the questions based on the discussions we had, especially in the last lecture, and also the questions from the module that I have given so far. Okay. Okay, so apart from the obvious application that a given function, its instantaneous rate of change can be measured by differentiating it, and the slope of the tangent at a particular point on the graph can be calculated by finding out the value of the derivative at that particular point. What else we can use differentiation for? So the first thing is that differentiation can be used to do what we call rate measurement, or as a rate measurer in physical problems, okay, or in problems related to everyday physics. So as a rate measurer. So we've seen a couple of problems based on this in the last lecture also, but let's understand this in more detail. So for example, in kinematics, or the study of motion, okay, for motion along a straight line, okay, let's say the x-axis, if position x is known as a function of time, then velocity is the instantaneous rate of change of position with respect to time. And acceleration becomes the instantaneous rate of change of velocity with respect to time. So let's say we have a numerical example like this, that a particle starts from rest at x equal to 0, at time t equal to 0. moving along the x-axis such that at time t equal to t is in seconds, its position x in meters is given by this relation, that x is equal to this kind of relation. Okay. So now we have to find its velocity as a function of time its speed at the instant 0.5 seconds, 1 second, 1.5 seconds. Its direction of velocity at the same 3 instants. And its acceleration at the same 3 instants. Okay, so let's work out this question based on the explanation given above, that we can define velocity as instantaneous rate of change of position versus time, that is dx by dt. And we can define acceleration as instantaneous rate of change of velocity with respect to time. Additionally, from this, we can also understand that speed is nothing but magnitude of the velocity at any instant. So just try out this question and send me the answers. Yeah, anybody got the answers? Yes, Shayan, that's correct. Very good. Ishita, correct. Adinath, correct. Um, Correction, Shayan, just check your calculation once more. Yeah. Yes, Akshat, correct. Only thing is you have to give the algebraic sign of velocity, right?
Yes, I missed the negative sign.
Yes, yes. Okay, okay, Adinath, correct. Very good. Okay, so I think most of you got the answer up to the third part. So let's go through this. Okay, so the position x is given to us as a function of time, as you can see. In fact, it's a cubic function, to be precise. Okay, where position is in meters, time is in seconds. So the velocity, the instantaneous velocity, as per the definition, will be the differentiation of position with respect to time. Or you can also write this as 6 into 1 minus t square. So here the velocity will be in meters per second because the time is in seconds and x was in meters. So this becomes my answer for the first part. Now I want to find its speed. So speed at a particular instant is modulus of velocity. So at t equal to 0.5 seconds, we can see that velocity is equal to 6 minus 6 into, So speed but when we are talking about 1 second, we can see so speed is 0. Whereas when we are talking about 1.5 seconds, we can see the velocity is 6 minus 6 into 1.5 square. Minus 7.5. So the velocity is minus 7.5 meters per second. That means the speed will become the magnitude of this velocity. So the speed is 7.5 meters per second at 1.5 seconds. This is at 1 second. This is at 0.5 seconds. Okay. But now you can also understand one thing, that from the expression of velocity above, you can see velocity is positive from 0 to 1 second, and velocity becomes negative after 1 second. And precisely at t equal to 1 second, velocity is 0. So it is momentarily at rest. So something like this is happening. If the particle is starting from rest at time t equal to 0, then as it moves along the x-axis, at some time which is less than 1 second, it has a positive direction of motion. But by the time you come to 1 second, it has come to momentary rest. And then after that, it's turned back. So at some time greater than 1 second, its velocity is in the negative direction. So this is the type of motion it's having. It's going in the forward direction, then coming back like this. So that's why. Okay, Siddharth, correct about the acceleration also. Adinath, correct. Okay. Okay, now about the direction of the velocity, you can see you have already got the answer, because you have calculated the velocity first for each of the 3 seconds. I mean, each of the 3 instants in the second part. So accordingly, the direction is either along the positive x direction if velocity comes with positive sign, or it is along the negative direction if velocity comes with negative sign. Or through this analysis also, you can clearly understand that in the second part, the direction at t equal to 0.5 seconds, it is along positive x-axis. Okay. At t equal to 1 second, it is at rest. So there's no particular direction. It's momentarily at rest. Okay. And for any time greater than 1 second, like 1.5 seconds, You can see that the direction is along negative x-axis. Yes, Shayan, exactly that's what we've done. See, I'll just minimize this a little again. We have differentiated the value of x with respect to time. So that is this step. That is given as the velocity, the instantaneous velocity. So this is velocity as a function of time. So this is velocity.
Yes, sir. Understood.
Yes, tell me, Beta.
No, sir. I divided throughout by t, x by t and 60 minus.
Oh, see, that will give you average speed, na, Beta? Average velocity. You
Yes.
understanding, na? It will
Yes.
give you average velocity from 0 to t. But we want instantaneous velocity, na? So instantaneous velocity kya hota hai? It is the instantaneous rate of change of position with respect to time. Got it, no?
Yes, sir.
So in other words, if you're looking at an x versus time graph, instantaneous velocity is the slope of the tangent at any particular point, whereas average velocity is the slope of the secant line. So if you divide it by the total time t, you'll get from 0 to t, you will get that secant line and its slope will give you the average velocity. Okay. Now like that, let's come to the fourth part. We want to talk about instantaneous acceleration. So the instantaneous acceleration is defined as the instantaneous rate of change of velocity with respect to time. So here it becomes differentiation of this expression 6 minus 6t square. So the instantaneous acceleration is minus 12t. So this is a kind of situation which as yet you would be unfamiliar with in kinematics because it's a variable acceleration. But when we move on to the chapter of kinematics after calculus this time, you will see that we'll deal with many such situations where the acceleration is what we call non-uniform or variable. Okay. So this is a case of variable acceleration. And you can also see one thing that the direction of the acceleration is always negative. Variable acceleration, and it is along negative x-axis. So that's why you can understand that from 0 to 1 second, velocity and acceleration are in opposite directions because velocity is positive and acceleration is negative. But after 1 second, they are actually along the same direction. After 1 second, the velocity also becomes negative. Acceleration continues to be negative. So that is why from 0 to 1 second, the speed is decreasing. Whereas after 1 second, the speed is again increasing. Anyhow, so here our acceleration will be in meters per second square because our velocity was in meters per second. Okay, and time is substituted in seconds in this expression. So again, you can see that at t equal to half a second, the acceleration is minus 6 meters per second square. So you can say that the acceleration has a magnitude of 6 meters per second square and its direction negative x-axis. Similarly, at t equal to 1 second, the acceleration is minus 12 meters per second square.
Sir,
Yes.
so can we leave acceleration is equal to minus 6 meter per second square?
Can we use acceleration is equal to, a little bit louder, please, Anshul?
Can we leave the final answer as acceleration is equal to minus 6 meter per second?
Yes, yes. In fact, that is the correct answer, no? Because we have asked for acceleration, not magnitude of acceleration. No? Okay, so we have to give the acceleration with the algebraic sign only. No? So the
Okay,
correct
sir.
answer is going to be minus 18, minus 12, and minus 6. This I'm just explaining how to interpret this minus 18. It means that it has a magnitude of 18 and a direction along the negative axis.
Sir, at t is equal to 0.5 second, a is
Yeah.
minus 6. That means direction is negative along with the x-axis. Then what does it practically mean with the particle or the object which is moving?
So see, practically what it means is that what kind of, for example, if it's a block that is sliding along the horizontal floor, which is frictionless. Okay. So we want to visualize this as in terms of Newton's laws, what this can basically mean. So this basically means that it has been given some kind of velocity like this earlier on. Okay. So because of that momentum, it's continuing to move in this direction. So at t equal to 0.5 seconds, we saw its velocity was how much? Its velocity was 4.5 meters per second along this direction, but its acceleration is negative. Its acceleration, the magnitude of acceleration is 6 meters per second square. So that means something must be pushing it like this. So there must be some opposing force, like maybe there's friction or there's somebody applying a force like this. Okay, understood this now, no?
So, matlab, due to this, eventually at some point, at 1 second, it becomes 0.
Yes, yes. Okay. And also because of this, if you check that before it becomes 0, also the speed is actually decreasing. So for example, if you check the speed again at 0.75 seconds, you'll see that it would have become less than 4.5. So by the time finally you're coming to 1 second, it's come to momentary rest. And this kind of force is continuing to act. Okay, and it's a variable force because the acceleration is variable. So after 1 second, what happens? This force is further continuously acting. So it starts moving along the negative x direction. Ishita, what are we generalizing?
Sir, why is magnitude of velocity equal to speed? Because distance and displacement need not be equal always, no?
Very interesting thing you have told, asked Ishita. Okay, so what we are talking about is instantaneous speed and instantaneous velocity. Okay, so they always have that relationship. That instantaneous speed is the instantaneous rate of change of distance with respect to time. Na? So it is distance in time dt divided by time dt. You understanding better?
Yes, sir.
So we can also understand like it is
But
moving
when we
along
talk
the
about
x-axis. That means it is moving along a straight line.
here, of course, it's along a straight line only. But even then, there is a difference between distance and displacement. Okay, so for example, if we look at from t equal to 0 to t equal to, in this case only, if you look at 1.5 seconds. Okay. So what is happening to distance in this interval? The distance is like this. It's going like this and coming somewhere here. No? So if you see the position at t equal to 1.5 seconds, just check it out. X was how much? It was 6t minus 2t cube, right? So at 1.5 seconds, so that's 9 minus, write it like this. So it's 1.25, correct? So this is x equal to 1.25. Okay. But we also know that at t equal to 1 second is made that turning now. So what was x at t equal to 1 second? It was 6 minus 2. It was 4. So if I look at the interval from 0 to 1.5 seconds, what is the distance traveled? The distance traveled is this whole thing. It's gone from 0 to 4 and then come back from 4 to 1.25. So it's traveled a distance of 4 plus 2.75. Correct? So 6.75 meters. But what about the displacement? The displacement is simply plus 1.25. Okay, but this makes a difference to the average speed versus instantaneous speed. So if I ask you what is the average speed from 0 to 1.5 seconds, we will divide the distance by 1.5. And if I ask you what is the average velocity, we'll divide the displacement of 1.25 with the time of 1.5 seconds. You understanding now?
Yes, sir.
Okay, Ishita, this point is clear.
Yes, sir.
So average speed is not necessarily equal to instantaneous speed. Average velocity. In general, it is not equal to average velocity. Okay, and particularly in a case where the direction of motion is changing, this average speed is always greater than average velocity. But as far as instantaneous speed is concerned, that is always equal to magnitude of instantaneous velocity. Because what is instantaneous speed? Distance traveled in a time dt divided by that time dt. No? So even in a curvilinear motion, a non-straight line motion, if you look at a very small interval of time dt, in that the displacement is like this. So from t equal to t plus dt, the displacement is like this. So the distance traveled in that very small interval is mod of ds omega. So instantaneous velocity, when we come to vector notation later, we will see is this. But magnitude of instantaneous velocity becomes speed because it is distance divided by time. Okay. So this is another, concept related to kinematics that we are understanding on the basis of instantaneous rate of change right now itself, right? Okay, so hope this point is clear to all of you, especially Ishita, this is clear?
Yes, sir.
Okay, very good. Now, Adinath's question is that from v equal to 6 minus 60 square at t equal to 0, we get v is equal to 6, whereas at the instant t equal to 0, it was given. So actually, in this case, what is happening is not that it's like the particle might have been at rest initially up to t equal to 0 seconds. Okay, but immediately after that, what is happening? There is a strong impulse which is acting on it. So immediately, if we look at the moment just after t equal to 0, okay, the velocity is jumping from 0 to 6. So this is a good question that Arinath has asked, that if we are getting the velocity as 6 minus 60 square, then how come the object is starting from rest? So what that means to say that it's starting from rest is that if you look at the velocity versus time graph, it is at rest up to t equal to 0. It was not moving initially, but then suddenly the velocity jumps to 6. Okay, and from there the velocity is decreasing with time like this. Okay. So if you look at the acceleration versus time graph, you understand why that's. Okay, so Adinath, hope this point is clear. Okay, so this must have happened because at t equal to 0, just at that moment t equal to 0, there is what we call a sudden impulse that acts on the object. Impulse is force multiplied by time. It's like, when a carom coin is at rest and then you suddenly hit it with your finger, okay, or your nail. So suddenly the state of motion changes from 0 to a non-zero velocity. Or when there's a collision, an object is at rest. Okay, an object is at rest, but then suddenly at t equal to 0, something comes and hits it. So as something comes and hits it, its velocity suddenly changes to a non-zero quantity within an instant of time. Because a large amount of force is acted for a very short period of time, That is the period of the impact. Okay. Right. Let's now look at the next level of question for differentiation as a rate measure. So that day, remember previous lecture, we had discussed about that expanding square type of situation. We had a square metallic plate that was expanding because temperature was increasing. So let's look at something related to that or something like that. Okay. So here what is happening is differentiation, in fact, chain rule can be used to measure the rate of change of a quantity that is the function, or that is, you can say, a function of another time varying quantity. Okay. So basically it's like this, that suppose x is some quantity which is a function of time. Okay. Here it need not be distance. Okay, it is just some quantity, some physical quantity, and it is a function of time. So it is instantaneous. Okay, so that means x is what we call an instantaneous quantity. Okay, and we have some other quantity y which is a function of x. So this is another physical quantity. Okay, which obviously depends on x. So we'll understand this with lots of examples. Okay, so now for finding dy by dt, that is the rate of change, instantaneous rate of change of y with respect to time, okay, we use chain rule. Okay, so y is a function of x and x is a function of time, or y is a function of time. Okay, so dy by dt will become, dy by dt will be expressed as dy by dx into dx by dt. Okay, or become g prime of ft multiplied by f prime. Okay. So one example of this we saw was last time itself. We saw that if we have a square, like a square metallic plate whose side length is a function of time, so we know the rate of change of the side length. Okay, then the area is L square. So to calculate the rate of area with respect to time, we have to use this chain rule concept. So that becomes 2L into dl by dt. So this is how the area is changing with respect to time. So this is this concept over here. So this is the application of chain rule, in a practical situation where we know that one particular quantity, say x, is changing with time as a given function, and some other quantity, let's say y, depends on x. So now how we can predict how y is changing with respect to time? So for that we need dy by dt. So we use the chain rule concept. So dy by dt becomes dy by dx into dx by dt. So this becomes a critical chain rule step. So this only you can see we have applied over here on the side, that area depends on L and L is some kind of function of time. So rate of change of area with respect to time is relationship between area and length, and then relationship between length and time. Okay. So this is something that we'll be using time and again in physics in various chapters, not just to do with motion and mechanics, but in all the future chapters, okay, like whether we are studying heat and thermodynamics or wave motion or in class 12 electromagnetism, etc. There's one very essential concept and application of differentiation, okay, as a rate measurer. Okay, so let's understand this with a more complex example today. Okay.
Sir, can you scroll up?
Yeah. Yeah, any doubt with this one?
No, sir. Just taking screenshot of
Okay,
the
just
note. Done, sir.
okay. Finished?
Yes, sir.
Okay. Okay, so let's see a more complex problem based on this compared to the square based problem. So we now have, okay, a spherical body. Okay, imagine this is a solid metallic sphere. Just to show its three-dimensional nature. So this is a solid metallic sphere of radius r and mass m. Now this is being heated slowly such that its radius is increasing very slowly with respect to time. At a rate of 0.3 millimeters per second. So at a uniform rate, in fact. So at some instant of time, if its radius is equal to 10 centimeters, then we want to find the rate of change of its diameter with respect to time. Then we want to find again the rate of change of its surface area with respect to time. We want to similarly find the rate of change of its volume with respect to time, because all these things will be changing with respect to time. And finally, we also want to find the rate of change of its density with respect to time. And for this part, it's given to us that the mass is, let us say, 5 kilograms. Okay. So in any question like this, when we just use the term rate of change, we always mean instantaneous rate of change. We don't mean average rate of change. Okay. So that is something that we should understand as a generality now, that whenever we use the term rate of change, it means, it doesn't mean average rate of change, it means instantaneous rate of change. This refers to the instantaneous rate of change. Okay. So for example, if I say rate of change of x with time, so what I mean is dx by dt. I don't mean delta x by dt, delta x by delta t. Okay. So in general, from now on, the term instantaneous rate of change, the default meaning of it is always, the term rate of change, okay, the default meaning of it is always instantaneous rate of change. If it is not mentioned what type of rate of change, then we have to take the default meaning as the instantaneous rate of change, d by dt. Whereas if we say average rate of change, then specifically it means average rate of change. We should not refer to average rate of change as rate of change. Okay, so hope it makes that clear. So here you will just use that chain rule concept that we discussed above. Okay, so each of these quantities, whether we talk diameter or surface area or volume or density, they are all functions of R. And R itself is changing with respect to time, such that the instantaneous rate of change of R with respect to time is uniform. So dr by dt is 0.3 millimeters per second. So from that, for example, we have to find the rate of change of diameter, the rate of change of surface area, etc. We'll just use the standard formula for each of these quantities. For example, very simple, you know, diameter is double of the radius. So that's the simplest of these. Okay. No fighting. Yes, Akshat, correct. Adinath, how have you come to the first answer as 0.66? It should be, see, diameter is double of radius, no?
Yes, sir.
So just apply the chain rule, no? So the rate of change will be double of rate of change. Okay. And about second and third part, no? You have to find the instantaneous rate of change when the value of R is how much? 10 centimeters.
Okay, sir.
So when you are substituting that R, just be careful that dr by dt is in millimeter per second, whereas R is in centimeters. So you have to either convert this to centimeters per second, or you have to convert radius to millimeters. Okay, so that you will get the answer in terms of, for the surface area, either centimeter square per second, the rate of change, or millimeter square per second. You can express in either way. Okay. So for example, for the first part, if I refer to diameter as capital D, so we have the formula that diameter is twice of radius. Okay. So rate of change of diameter with respect to time will become twice of rate of change of radius with respect to time. So in fact, here you can see that the rate of change of diameter is also uniform with time because rate of change of radius is uniform. So the diameter increases uniformly with time at the rate of 6 or 0.6 millimeters per second. This is also uniform because this one is a uniform rate. So basically the interpretation of this statement is that dr by dt is a constant value of 0.3 millimeters per second, which we can also write as 0.03 centimeters per second. Yes, very good. That's correct now, Ajinath. So for the second part, let's say we write the surface area with the symbol S. So we know that S is equal to 4 pi r square. So this is a formula that is known in geometry. Okay. Now, interestingly, this is a formula that we can also derive by calculus. So when we learn about integration, we will see this, how we can prove that the surface area of a sphere is 4 pi r square by integration. But currently, let's just use the formula. Okay. So the instantaneous rate of change of S with respect to t, we will have to write like this. Okay. So that is differentiation of the quantity 4 pi r square with respect to r multiplied by dr by dt. Okay. Or another way of expressing this is that S is equal to 4 pi r square. So ds by dt is equal to differentiation of this quantity 4 pi r square with respect to time. So that is the same thing as this chain rule. So next step, into dr by dt. So the instantaneous rate of change is 8 pi r into dr by dt. So what we notice here that this is going to be a variable rate of change because r is changing with time now. So this is going to be ds by dt will be a non-uniform rate. Okay. Because it's proportional to r and r is changing with respect to time. So at the instant when r is equal to 10 centimeters, the instantaneous rate of change of surface area will become 8 pi into 10 centimeters into, now I'll convert this and write this as 0.03 centimeters per second, so that I get my answer in centimeters square per second. So this will become how much? 0.3 into 8, so 2.4 pi centimeters square per second. Okay. And if I want a more exact answer, I can just substitute pi also as 3.14, or I can leave the answer this way, it's fine. So you can see that from instant to instant, the value of ds by dt is changing because the value of r in that formula will be changing, 8 pi r dr by dt. But on the other hand, the rate at which the diameter is changing, that is a constant. That's a uniform rate of 0.6 millimeters per second. Okay, Ishita, just check the unit of your third part. Okay. That's correct. Okay, so if we express this in millimeter square per second, we can see this will become 240 pi millimeter square per second, because 1 centimeter per second is 10 millimeters per second. Sorry, 1 centimeter square per second will become 100 millimeters square per second. Now let's come to the third part, how the volume is changing with respect to time. So the formula for volume in terms of radius is 4 by 3 pi r cube. Okay. So now rate of change of volume will become rate of change of, okay, that we can write as d by dr into dr by dt, or basically saying this. This we're using here. So this becomes 4 pi r square when we differentiate into dr by dt. So this is a general formula of how the volume is changing with respect to time in terms of dr by dt. So here also we can notice that it's a non-uniform rate. Okay, so again we have to calculate this at the instant when r is equal to 10 centimeters.
Pi.
Yeah, you see this will become 4 pi into 10 square into 0.03 in centimeter cube per second. So that will become how much? 12 pi centimeter cube per second. Or you can also express this as 12 pi into 10 raised by 3 millimeter cube per second. 1 centimeter cube will be 10 raised by 3 millimeter cube. Now, what do we do about the density? Anybody has done that calculation yet?
And mass upon volume
Yes, mass upon volume.
and quotient rule.
Sorry?
I have applied the quotient rule, sir.
Acha, you are applying the quotient rule. You can do that also. But that's not required now, beta, because m is a constant now. Following my point?
Yes, sir. Yes,
So,
sir.
so only volume is the variable, no? So it's in the denominator, but you can bring the power with the minus sign above, no?
Yes,
So
sir.
there are a couple of ways. Now you can express the volume as 4 by 3 pi r cube. So you can express the density as a function of r. Okay. So it will become proportional to r to the power minus 3. Or you can just keep it as a function of v. It will be proportional to v to the power minus 1. And then you'll have to use this thing, the rate of change of volume, which you have calculated at this instant is 12 pi cc per second. So either way you can do it. Okay. You can express the density as a function of volume, or you can go one step further and express it as a function of radius.
Sir,
And
how can we say that it is 12 pi cc per second, because we are calculating it at 10 second. Now r is equal to 10 second or 10 centimeter.
हाँ तो वैसे है ना, देखो 4 pi r square into dr by dt ना. Now r को मैंने क्या सब्स्टिट्यूट किया, 10 सेंटीमीटर. सो ये वाला जो क्वांटिटी है इसका यूनिट क्या है, सेंटीमीटर स्क्वायर है ना, 10 स्क्वायर. और dr by dt को मैंने क्या सब्स्टिट्यूट किया, 0.03 सेंटीमीटर पर सेकेंड. सो r square into dr by dt, what the unit of this is becoming, centimeter square into centimeter per second. So that's how we are getting cubic centimeters per second. Is it clear, beta?
Okay.
So that's the thing we have to be careful, that we should not substitute, for example, r in centimeters and then dr by dt in millimeters, because then we will not get some consistent unit. So either both are in millimeters and millimeter per second, or both are in centimeters square and centimeter per second. Okay, so let's come to the fourth part. So to avoid confusion with diameter, we'll use the symbol rho for density. Okay. The same symbol that you used to use for resistivity in current electricity. We'll use that symbol over here. So density is mass per unit volume. So we can use either this or we can use this. So if we use this, then we'll say that the rate of change of density with time will become the rate of change of density with respect to r into dr by dt. Or if we use this, we will say that the rate of change of density is rate of change of density with respect to volume into dv by dt. So let's go with this method first. So density is equal to mass per unit volume. So this will become mass multiplied by minus 1 by v square. So the negative sign is actually showing us that the volume, the density is decreasing with respect to time. Okay, so this is the formula that we get for rate of change of density And the minus sign is just showing us that as time is increasing, because the radius is increasing, so the volume is increasing, so the density will be decreasing with respect to time. Okay, so at an instant when r is equal to 10 centimeters, okay, volume is equal to 4/3 pi into 10 raised power 3 cubic centimeters. Okay, and dv by dt we had just checked out above. That was equal to how much? It was this quantity, 12 pi cubic centimeters per second. And mass we have taken as 5 kgs, right? Yes. So at this instant, when r is 10 centimeters, we'll substitute this in this. So you'll get the rate of change of density with respect to time will become minus 5. Let's convert this to grams. Upon square of the volume. So that is so the unit will become centimeter to the power 6 into dv by dt, which is 12 pi in centimeter cube per second. So this will come out to be now the unit of this becomes grams second per centimeter cube or gram per centimeter cube per second, like this.
So it will be 5,000 into 9.
Sorry, into 9. That's correct. Okay. So how much is finally becoming? This is becoming is becoming 27 by 4 pi into 10 raised power minus 3 gram per cc per second. But don't forget the minus sign. So the density is decreasing at this rate. At the instant when r was equal to 10 centimeters. Okay, so obviously a bit of algebra involved over here in the calculation, or more like bit of arithmetic involved in the calculation. Okay.
Sir,
Yes.
Sir, the density is mass by volume. So can we find it in terms of radius and differentiate it with respect to radius and multiply it by dr by dt?
Exactly. So that is the second method we have. That's also equally correct. Okay. So that will be this second approach. Okay. We could have taken this approach, which we have done over here, or we can still take this approach also. Correct?
Okay,
This is
sir.
what you are saying?
Yes, sir.
I express the density in terms of mass and radius, because volume itself is a function of radius, and then write it like this, that it is rate of change with respect to radius into dr by dt. So if we go, let's see, we should get the same answer if we use this. So this will become, now let's differentiate this term. So 3m by 4 pi into differentiation of r to the power minus 3. So that will be minus 3 r to the power minus 4. Okay. So this should become minus of 9m by 4 pi r to the power 4 into dr by dt. Okay. So this is the formula that I'll get for rate of change of radius, rate of change of density with respect to time. Now you can actually show that this formula is equivalent to this formula here, but we'll do that by substitution. So now we want to find at the instant when r is equal to 10 centimeters. Okay. So when we substitute r equal to 10 centimeters and dr by dt in centimeters per second, you should get the same numerical value as we got before. Okay. And also m as 5 kgs, of course. So just do the substitution, I'll show you.
Sir,
Right. So let's do the substitution. So that
sir,
will just show that this equivalent method is ultimately the same. So minus 9 into 5 kg. Yes, Srijita, you have a question?
yes, sir. Sir, how did you get m into minus 1 by v square?
Sorry, why did we?
Why? How did you get m into minus 1 by v square? The first one.
Acha, that one, no? Okay, see. I'm differentiating d rho by dv now. Okay, so I'll just take that aside here. Okay. So density is mass by volume. Okay. So that is mass into volume to the power minus 1. So when I'm calculating this now, that is differentiation of this with respect to volume. Now remember here mass is what? It's a constant.
Yes, sir.
You got it now, no? Okay, so power rule. So minus 1 into v to the power minus 1 minus 1.
Yes, sir. Thank you, sir.
Very good. Okay. All right. Now coming back to this. So mass is this much, 4 pi. Okay. Into the value of radius we are taking at that instant is 10 centimeters. So this will become 10 centimeters to the power 4 into dr by dt, which will take as 0.03 in centimeters per second. Okay. So at least the unit is checking out, you can see. So it is minus 9 into 5 into 3 divided by 4 pi. Okay. Into what power of 10 now we get. In the numerator, we have 3 minus 2. Right. And in the denominator, we have 4. So that should give us the same thing. Let's see. Getting something different. No? Oh, I think I missed out the 5 here. So it's 27 into 5. This term is, in the numerator it is 27 into 5. Okay. That's how much now? 135. So here also it should be 135 by 4 pi into 10 raised power 1 minus 4. So that's minus 3. And the same unit, because it is gram per centimeter to the power 4 into centimeters per second. So it is gram per cc per second. But again, more importantly, with the minus sign. So at this stage, you might feel that the second one is more convenient for us, because we have to just directly substitute the value of r and dr by dt. Whereas in the first one, we have to first calculate the volume, because we had v square in the denominator. So we have to separately calculate the volume as 4 by 3 pi into 10 raised power 3. Then substitute that here. So, but it's more or less the same. Both methods are equally efficient. Excuse me. Okay, people. So hope this question is fully clear. Now we come to another level of example, okay, where there is bit of, let's say trigonometry involved in the geometry. Okay, here the geometrical formula was just volume in terms of radius or surface area in terms of radius. But now let's see an example like this. So for example, in trigonometry, all of you have heard the term angle of elevation, right? If we have a point which is elevated from the ground, okay, and we are observing the point from a certain distance. Let's say this is a particle P, okay, which is at a certain height from the ground. But as an observer, we are present somewhere here. So then that point has what we call an angle of elevation, right? That is, when we look at that point directly, we are looking at, our vision is at a certain angle with respect to the horizontal. So this is called angle of elevation. So theta here is the angle of elevation for the point or particle, whatever P, with respect to the observer shown. So if this horizontal distance is d from here to here, yes, and the height of this particle is, let's say, y, then theta is equal to what we said, tan inverse of y by d. Okay. Or in more simple language, we can say that y by d is equal to tan theta. Now suppose in this problem what is happening is that this particle is actually moving down. Okay. So the particle P is in free fall. So it's moving down along the direction of gravity. So at a certain instant, okay, its instantaneous speed downwards is, let us say, 12 centimeters per second. When the value of its height with respect to this guy's eye level, that height is equal to, let us say, 15 meters. Okay, and capital D, which is a fixed distance, that is given to us as, say, 20 meters. Okay, the observer is not moving. Okay, so the observer is at rest. So we want to find two things here. One is the rate of change of the angle of elevation. That is, we want to find d theta by dt. Okay, and we want to find the rate of change of the distance between the particle and the observer. So we can say that is ds by dt, where this is the instantaneous distance from the observer to the particle. Okay. So we'll look at this next. So when we are solving this problem, basically we'll have to use this relationship, the relationship between y and theta, to find out d theta by dt. Okay, and we'll similarly have to develop a relation between s and y to find ds by dt. Okay, but just by looking at the problem, can you tell me what should be the algebraic sign of d theta by dt? Should it be positive or negative?
Positive.
Or negative.
Negative. Now you can see as the particle is coming down, the angle of elevation is decreasing. So like, let's say initially it was here. So the angle of elevation is like this. Now after some time, the observer is stationary, but the particle has come here. So you can see the angle of elevation has decreased. It has become theta minus delta theta. So you can see that this should be a negative quantity. When we calculate it, it should come out as a. Similarly, you can see that distance is decreasing because the hypotenuse of this triangle is decreasing. So expectedly, we should get ds by dt as also some negative quantity. Okay. So that is one thing. And the other thing is, how will we relate the speed of this particle or the magnitude of the velocity 12 centimeters per second with respect to y? What is the relationship between these two things?
Distance and speed.
So what is the relationship between y and v? Y is the position of the particle with respect to this fixed point, and velocity is what? The rate of change of position, right?
dy by dt.
Yeah, so dy by dt should be what quantity? Plus or minus?
Sir, minus.
Minus, because y is decreasing, you can see. So the important thing here is when we interpret the relationship between y and v, so the instantaneous speed v is actually the rate at which y is decreasing. So it is minus dy by dt. Or you can say dy by dt is minus of 12 centimeters per second. Okay, so use these two things I've told you just now to just try and calculate this. Okay, one is directly this relationship is there. So we can use chain rule in this. And in this relationship, when you use chain rule, remember capital D is a constant, but y is changing with time in such a way that dy by dt is equal to how much? Minus 12 centimeters per second. Okay, so as I said that here dy by dt is minus of v because y is decreasing with respect to time. At the rate of v. Okay. So now first part you start with this formula. So tan theta is equal to y by t. So differentiate both sides with respect to time. So differentiation of tan theta with respect to time is differentiation of y by t. So next step, when you differentiate tan theta, you have chain rule. Okay. Whereas on the other side, you just have y, capital D is a constant. Okay. So this is where we are executing from here to here. We are executing the chain rule step. And of course, all of you know the formula of differentiation of tan theta. So just implement that now. Okay. So another thing now will be that when you actually do the calculation and substitute the values here, you'll need to substitute theta. So for that, you already have the value of y and d at that instant. So it is a known triangle. See, it is a 20, 15, 25 triangle. If you calculate the hypotenuse, so it's a 3, 4, 5 type of triangle. So you know the angle involved in a 3, 4, 5 triangle. Now, you must have learned that in vectors, right? You've seen 37 degrees and 53 degrees, right?
Yes, sir.
So that's just a hint that this is that type of a triangle, because the base is 20 and the perpendicular at the given instant is 15. So the ratio of base to perpendicular is 4:3. So it's a 3-4-5 triangle.
Sir? Excuse me, sir. Sir?
Yes, Rijita, we can differentiate that term, but that will help us for the second part, right? For calculating ds by dt. So for the first part, we will still use, we need d theta by dt, no? So we need to relate theta, right?
Yes,
Let's
sir.
complete the first part. So tan theta is y by d. So differentiation of tan theta with respect to time is this. So because capital D is a constant, so we can just bring 1 by d outside. So this is our relationship, that sec square theta into d theta by dt is equal to 1 by d into dy by dt. So now we want to find d theta by dt, dy by dt is given to us. So d theta by dt will become 1 by sec square, that is cos square by d. So this is the relationship between the two rate of changes. Okay. Now at the instant, we are given, at that particular instant, the value of y is 15 meters. The value of capital D is of course fixed, and that is 20 meters. And this downward speed v is 12 centimeters per second. Okay. So our dy by dt is minus v. So that is minus 12 centimeters per second, or you can write that as minus 1.2 meters per second. And we can also see our instantaneous value of theta. It is tan inverse of 15 by 20, or tan inverse of 0.75, which we know is 37 degrees. So at that particular instant, when y is equal to 15 meters and v is equal to 1.2 meters per second, at that instant d theta by dt becomes cos square 37 degrees divided by 20 meters into minus of 1.2 meters per second. So as you can see, unit wise meter will cancel, so we'll get in per second. So that is basically d theta by dt in radians per second. So this is 0.8 square by 20 into 1.2. So that is so the minus sign significance of that we already know. So you can see the angle is changing at comparatively a very slow rate. Yeah, Srijita?
Sir, we had started with degree. How did we get radians?
Sorry, how we had started with?
Degree. How did we get radians?
I'll explain. Okay, how we got radians. Now see, we have substitute 37 degrees in the formula for cos theta. Na? But cos of theta is a dimensionless quantity here.
Yes, sir.
Cos 37 or cos theta, this is unitless. Okay, so what is the unit of our quantity d theta by dt? Its unit is basically this unit, meter per second, divided by the unit of 20 meters in the denominator. So it is in per second. Okay, so it is in so much angle per second. Now what is the SI unit of angle? It is radian, no?
Yes, sir.
So that's why it's radians per second.
So we need not convert.
If you want to convert to degrees, you can always convert to degrees. Okay, so if I'm getting x radians, that is equal to how much? It is equal to x into 180 by pi degrees. Okay, so that means this can also be converted. This can be converted to minus 0.038 into 180 by pi in degrees per second. Understood my point, na beta?
Yes, sir. Sir, but if it's unitless, we could have taken degree per second as well.
No, see, that is the point. See, how we define angle? We define angle as ratio of arc upon radius. Na?
Yes, sir.
So when we actually divide the arc in meters by radius in meters, or whatever, centimeters by centimeters, we get theta in what unit? We get it in radians. No?
Okay, sir.
So that's why. So radian is actually the unitless, or what we say, dimensionless unit. Okay, so this angle that we get from the simple ratio, it is in radians. Then we can convert it to degrees by multiplying with a factor of 180 by pi. Okay, so this part is clear, no? Now let's look
Yes,
at how
sir.
the distance is changing with time. So for rate of change of distance with time, now we can use either of the two things. We can either use Pythagoras theorem, because we know dy by dt, so we can find s as a function of y and then differentiate that. So ds by dt will become this, okay. Or we can also find s as a function of theta, okay, because we know d theta by dt also. So this will become derivative of that function into d theta by dt. Okay, so if I go with this method, I have s is equal to square root of d square plus y square. So ds by dt is differentiation of square root of d square plus y square. So that is this into dy by dt. So next step, to differentiate this first term here, I'll have to use chain rule. So it's derivative of square root. So 1 upon 2 times square root into derivative of this whole term. So that's 2y into dy by dt. Okay. So that will leave me with y upon square root of d square plus y square into dy by dt. So this is the relationship between rate of change of s and rate of change of y. And we'll substitute it and calculate it. But just a moment before that, you can see that this method here is going to be easier, the second method. So in the second method, we can just express s as capital D. So we have d by s is based upon hypotenuse, so that is cos theta. So we have this as d sec theta. Right, this is correct. So why we are writing it like this? So that we don't involve y, because y is changing with time. So we are expressing s as only a function of theta. That makes it simple for us, right? So ds by dt is so that is d into rate of change of sec theta. Okay. Now you know that sec theta's differentiation is what? This. That will become this. Okay. So this becomes a formula in terms of theta. Okay. Now at the given instant, what is happening? Y is equal to 15 meters, theta is equal to 37 degrees, and dy by dt was minus 1.2 meters per second, or d theta by dt, we had seen above, was minus 0.038 radians per second. So you can use all this information. So this is 15 by 25. Or if I use this, So this should also give you the same. So let's just check out the calculation. 20 into 15 into 0.038 divided by 16. Yes. So this is a bit of an approximation over here. There were more places in decimal. So if we use the exact value in the fraction, we'll get. So this one's exact value. Actually, this. Okay. People, only one thing you might have noticed that I have actually made a mistake of unit here. I've written 12 centimeters per second as 1.2 meters per second. So that is wrong. So let's take this as 120 centimeters per second. Okay, so then the calculation I have done will become correct. So here we'll change this to 120 so that I don't have to change the answer. This remains 1.2. Okay, so hope the method of calculation is clear.
Sir,
Yes, beta.
sir, how did you get 2y?
How did I get?
2y in the first part.
Achha, this now. Okay. So again, see, this part is a separate application of chain rule. I'm differentiating this thing with respect to y now. Got it now? So what I'll have to do that now? See, differentiation of this with respect to y. So how we'll do that? Chain rule. So take d square plus y square as z. So then this square root of d square plus y square is root z. Okay, no? So this will become differentiation of root z with respect to y. So that is differentiation of root z with respect to z into dz by dy. Right now?
Yes, sir.
Okay.
So here rate of change of acceleration will be 0.
That we don't know, beta. Because see, we don't know whether velocity is uniform or not now. You understanding the point? It was just given that at that instant the velocity is 1.2 meters per second. Okay, no?
So because it is in free fall and the acceleration is constant.
So if it is in free fall, yes. If we assume that in free fall there's only gravitational force acting on it, and like we can neglect air resistance, like drag forces and all that, then yes, we can say that the acceleration is 9.8 or 10, whatever the value of G is.
Okay,
Got
sir.
my point, Navita?
Yes.
Anyway, this differentiation step is clear. Differentiation of d square plus y square with respect to y will become 2y. So that's how we got this.
Yes, sir.
This direction. Okay. So lot of questions in your worksheet, sorry, in your module exercise 3 are based on this principle, differentiation as a rate measurer. Okay. So you have to complete that set of questions, and along with that, I will also be sending you an assignment this week again. The assignment will have some revision questions for techniques of differentiation, like application of chain rule, application of product quotient rule, and all this, so that your method of solving differentiation thing is like properly revised. You also have a test coming up on 6th, right? So that test will be up to methods of differentiation. Okay, so chain rule, up to chain rule concept, you should be very well revised before that test. Okay. Anyhow, so we'll conclude the session here today, and next time we will start looking at further applications of differentiation, where we'll see how we can find the behavior of the graph of a function, right? Things like maxima, minima, etc. of a function using differentiation. Okay. So hope today's lecture was clear, and thanks for attending, people. That's it for now. Okay.
Thank you, sir. Bye.
Okay, bye, people.
Thank you, sir.